Hi, everybody. This is the second part of our series of talks about high-performance data science with modern C++. In the first talk, we covered Zooskling and G3P, which you can find the video for the previous recording here. And as it says here, as we have more, including this one, I put the video recordings here as well. Uh, but the things that we are going to cover in the second talk is actually more about randomness. But first, let me update some of the things that we have about Zooskling. So let me show you here. When I had my first dog, one of the complaints that I received from my, colleague Paul, which is also here, was that it's the Zooskling is good, but the problem is that it's not updated for a while. Yeah, and it just the last standard supported by Zooskling was C++17. So I remember I told him that I'm gonna try to, see that if I can put some of the patches in the, repository and make it work for higher versions. And actually I succeeded. So if you check here in the release, the releases that we have, the previous one was version 1. I tried to put this version in accordance with the Kling version that is included. So it was the Kling 1, but the development version, which supported the CUDA stuff in the previous, the image that I had. Now in the end, that one uses the LLVM 13. And the Ubuntu was 20. So in order to make it work for LLVM 16, which is Kling 1.1, I had to upgrade the Ubuntu version included in the image, I mean the Docker image, to 22.04. So these are the latest version in that one. And because of that, now if you try to use the Docker image, we 1.1 now, you can through experiment with C++20. So if I show you here, if you remember from the previous time, these are the things that we had. I added a new page here for C++20 support. It's actually automatically tries to run them. You can, if you remember, you can also click on this button to, run this on the binder. But, the running are actually there. So you can see here that this is a std span, for example, which works as I just got some of these examples from the C++ website. I mean the reference one. And you can see the output is in accordance with that. This one is the ranges. You can see that C++ 20 have these things and more. And I also tried concepts, it works, but I'm not sure about the full coverage or not. And this one is a three-way compare that I put here, some of the things that I just dropped it here to see if it works. And it seems that it works. So, but maybe some of the stuff not. I think the more complete support for C++20 is in Kling 1.2, which is also in the repository, but they didn't release a version for that. And that one is based on LLVM 18 rather than 16. For the next one in this series of talks, I try to compile that as well and see if I can succeed or not. But if I do, I put it here. I think that one, the support for C++20 will be even more than this one. Having said that, the things that we actually want to cover for today is randomness with ranks. So when you work with data science projects, there are many times that you need gazillions of good quality random numbers, and usually you need them fast. So why not to get them in parallel using a library that can do that? And that one is Ranx. As a reminder, back in 2023, I developed a parallel random number generator library, P2RNG, uh, and delivered the Compute Ontario colloquial talk about it. You can watch the video here. But now I just rebranded it under a new catchy name, Ranks, and put some more features there that I'm going to cover. And it also supports the zoo-scaling and outputting randograms and also histograms, which are really cool for random numbers and cool for data science things. And said, why not we put this one as well here? So to do that, let's switch to Ranks documentation page, which has all the things here, like G3P and Zooskering that we had before. You can run them on Docker and Apptainer or on the binder as well. If you click on this link, it works. Maybe not that I click this here because it takes maybe some time, but it's already cached. It says the GitHub service unavailable, maybe because of the problems but it works in the background. Let me see. It's working now. So while it works, another thing that is interesting, that we have a new thing on our new cluster NIBI, which is open on demand. Because of that, and because AppTurner is there, we can easily try all these images, I mean Docker images, using AppTurner on it. So you already probably familiar with this, but you can have a compute node or login node. I've actually registered for a 2-hour on compute node using the GPU. So you can, once it's allocated and running, you can just launch it. I've already launched it here. So when it's like that, you just need to module load Apptainer, which is, I've already done that here. But after that, for example, if you want to run this, you just need to copy the Apptainer version here and just paste it here. So I've already have it here. So once you've done that, and the good thing is that the Apptainer can cache these images. It's already cached this image for me. The only thing that I need to do is to press Control button and click on this. It takes, I don't know why, it takes some time on this. On my computer, it's instantly, launch the Jupyter. But on open on demand, it takes a while. I don't know why, but it's there. So you can try the samples here. For example, this one, and this is so for this, I need to switch to actually this one because it's from previous one. Let me go. This one is for the images for CUDA and those things, but for the ranks, the samples, I have them here, but I need to go a level down, I think, here to development, and then ranks, and then examples. Actually, the docs are here and notebooks. In the Docker image, they are already included, but in the Apptainer, you should tell it to not mount the home directory, which actually automatically it does, and then you can see that. But no problem, I have them here, and I can open. So this is the way that you work on the NIBI like this. And if you, I think by now the Jupyter lab must be here, yes. So you can follow the whole things here and run them, because on the web page, some of these samples, the output are already included, but some of the examples that we need interactively, manipulate may not. So I have it here, and but switch to our web page here. So what is Ranx here? Ranx is a next generation parallel algorithmic or pseudo random number generator. It, it's now available both as a utility. It can be, because it's multi-platform, you can compile and build this utility for Windows, Mac, and also Linux. That generates random numbers, and also a library, that header-only C++ library that supports different APIs like OpenMP, CUDA, ROCm, and one API. And it can generate this on all platforms. So it supports both CPU and GPU. You can see the different version for different APIs here. This is the serial version using the standard C++ library facilities for random number generation. And this is these are the Ranx version of it for different APIs, OpenMP, CUDA, and one API. And one feature that we are going to cover about it is that it plays fair. It means that no matter what's the underlying hardware or platform, if you use the same seed distribution and also engine, you on all these platforms, you always get the same sequence of random numbers. It's really important for unit testings and other things. And one of the reasons that I developed this library is that during working in other projects, I realized that it's not really easy to have something like that, and most of the libraries don't support this. So as you can see, it's multi-platform, supports Linux, Mac OS, and Windows. And more about that, about the engines included, and also the distributions in it comes next. It has also the unit testings and Google benchmark and everything. But to start to work with it, you need just a C++ compiler that supports at least C++ 17 standard, and also CMake 3.21 or higher. If you want to do the unit testing and Google benchmark, you need the Cache 2 or Google benchmark, but you don't have to install them, because the CMake script automatically tries to download and configure them if if it cannot find installed on your system. So that in order to start working with it, it's a regular CMake building thing. You first clone the whole repository and then try to use the CMake to build, configure, build, and install it. And when you do that, it automatically also installs the Ranx utility. Here, there are some more things. If you want to run the unit tests or benchmarks, there are some, you can use these things. And if you want to develop with Ranx, the best way is to use the CMake, because it has a nameless-based CMake targets that you can easily compile for your code for different platforms. The way you do it is like this. You can do the find package thing, and then use this sample CMake, code snippet to do that. Or you can use the embedding with CMake using this way. If you try this way, for example, if it cannot find the thing, it tries to automatically fetch the content and download the ranks from the repository, install it, and then you can have the whole thing in your project like this. You can also do the rapid prototyping with Jupyter, like the way you do. These are the things that you need to know. As I mentioned, the Conda version of the Zscaling doesn't support the new things like, for example, C++20 or OpenMP or CUDA. OpenMP is required at least for ranks. So if you go with this one, it probably doesn't work. So I think you have to switch to the the Zscaling version that I provided as an image here to work with this. And these are the Docker and Obtainer way of using. As I mentioned, there is a Ranx utility included in the whole package. When you do the CMake and install, this utility also automatically installs. I made it there is a Ubuntu utility, which is called rand, which generates the random numbers for you, and using this, some options. I try to have the Ranx utility to work exactly like that, but generates the numbers in parallel. The only exception is when you ask to generate unique numbers. In that case, it goes into the serial version. I think in the future versions, I'm going to also implement the parallel version for the unique one as well. But you can see the output here. Every time you run this, it generates a new number or sequence depending on what you ask. I can also show you here, for example, if I go to terminal, it's already included in the image. So if I do this, you can see each time it difference random sequence unless you go with a seed. So if I mention a seed like this, then every time you get the same sequence. But the important about the Ranx version is that no matter you are on Linux, Windows, or Mac, or using the GPU or OpenMP, you always get the same sequence like this using the same seed. And that's a feature that you can't easily find for in other random number generators. Why? You will find out next in our presentation. So before going to the detail of working with Ranx, we need some background about the randomness, which is some of the things that we are going to cover here may be obvious, but some of them may be interesting even for someone that works in this field. So we have different types of randomness: physical, algorithmic, and quantum one. The physical is the one that some people call it true randomness. It's based on the physical things like, tossing a coin, rolling a dice, and those things. And most people feel that this kind of randomness are, way better than the algorithmic version. But if you check, for example, this article that I, put it here, they found out the fair cones tend to land on the same side they started. So the thing is that even for the physical randomness, it may not be as random as you think. But algorithmic ones, it's an algorithm in computer that generates this sequence of random numbers. And the good thing about them is that they are blazingly fast. They can, especially if you use for GPU, for example, GPU and those things, they can generate lots of random numbers in a fraction of a second. So that's why we use it, and that's why I like the name algorithmic, random number generators rather than pseudo, because it's not pseudo, it's just a sequence that you generated in computer. And we have a quantum randomness, which is based on the quantum physics. For example, electron polarization of photon and also electron things. And this one is actually the real one, but the quantum computers may not be available for at least we should wait for 5 to 10 years to have them in our at our hands. So the thing that we are going to cover here is algorithmic random numbers, or ARNGs, or some, as I said, some call it PRNGs, or pseudo random number generators. Um, you can see the history here, but what I'm going to emphasize here is that let us learn what these random number generators or algorithmic ones do under the hood. So here is a super simple, super fast Lemur 64 engine that I put it here to demonstrate the three parts of an random number generators engine. If you check that the history, the name Lemur is come from this, but they are really common. They are based on the linear congruential generators, or LCG generators. The three parts or three components of this are first the engine state, and then the state transition function, and output function. You can see all of them really clearly in our Lemur engine here that we implemented here, or I put it a version of it here. So this one is the engine state. As you can see, it uses an 128 bits integer for the state. This part is the state transition function, which advances to the successor state. And the last one is the output function, which map the unsigned to unsigned integer values. For example, this one is doing but shifting 64 bits. This is the all things that you can see in action in an engine. If we want to make it in a working form, the only thing that we have to do is to change it to a struct like this in C++, put a constructor using a seed, and usually for LCGs you need to provide odd seed. So it tries to change every seeds that are not odd to an odd version, and then we overload the function operator like this. So next we can have instantiate an engine like this. And if you want to get a random number, we just call like this, and it gives us a random number. Each time you run this, you get a different number. So for example, if I want to show you here, I didn't have it here. What about the, okay, let me get back to this. So here's the Jupyter version of the whole thing. So I try to run this for you to see that each time I run, let me make it a little bit bigger, I get a different number. So let me put this one close to this. Sorry. Okay. Now the next thing is that there are some important attributes of an ARNG that we refer to them. So let's learn them, but now we can learn them really easily. First is output bits. So for example, when you say usually that output bits comes into the name. So when we say lamer 64, it means that the integers that we get from the engine are 64-bit byte. And the other one is period. Period is the smallest number of steps after which the generator starts repeating itself. So you can see that because the state of this lamer is 228, the number of the steps is 2 to the power of 128. So they usually express it in the as power of 2. So for this engine that we developed here, or we didn't, we just used here, the period is 128. So the number of steps after it resets is 2 to the power of 128, which is really big. And the next thing is state. We already see what it's just changed the initial value that determines the sequence of random numbers. By changing that, you get this different sequence in the whole period. And finally, footprints, also known as space usage, is the size of the internal states in bytes. So you can see that for our engine, the internal state is 128 bits, and if we divide it by 8, it means that it's 16 bytes, the footprint. So how big is Mersenne twister footprint, which is a really known random number generator in computer science? Uh, it's interesting to know that it's really huge for Mersenne twister. Is 624 32 bits integers, which makes it 2000, more than 2000 bytes. And even the 64-bit version has the exactly same footprint. But how we can know that the numbers generated by for example, the engine that we used here are actually random? And this question is really, really hard to answer. And because of that, there are, different batteries of tests, statistical tests to do that. The first one was Die Hard, and then another version came called Die Harder. And the gold standard now is Test U01, which includes 3 subsets: small crush, 10 tests, crush, 96 tests, and big crush, 106 tests. So to be a good random number generator, it's not just sufficient to pass big crush, but if you do the engine can't pass the big crush, there is a problem with it. And another fact check here, which one passes big crush? Do you think the Mersenne twister or the Lemmer 64 that we had it here? It's rad even for me to know that the Mersenne twister, which is so extremely popular and widely used ARNG, does not pass big crush. It fails 2 tests because of its linear recurrences. But the Lemmer one that we included here, it passed the big crush. So the things that we use are not usually the thing that we think they are. So that's an interesting fact. Even this, the small, engine version, which is much, much faster than Mersenne twister, can, pass the big crush. So we are not going to, do the big crush test for this Lemmer 64 here, but what we are going to do to show you some of the ways that you can check the statistical correctness of your engine is the first one is visual analysis by randogram. So uh, because we have the G3P in the previous, talk, we covered it, and the new plot has the RGB image feature that we can use to generate a plot. We can easily generate a randogram for our engine. This is the code that you can see that does the thing. And if you check here, we use the same engine. We use the same engine that we had on top. But because it generates the random numbers in an arbitrary range, we need to bring it to a range. And we use the modulo operator, which is really common, to bring it to the range of 0 to 255. And this is the resulting randogram here. You can see that you can't see any special pattern or those things. And if I try to run it here, you can see that that one already generated. You can see this, and you can even send a longer sequence. We learned how to have the animated GIF or WebP in previous talk. We can have a for loop to make a white noise of this. So if we run that, it takes, because it's 10 frames, for example, you can go for less or more frames. It may take some time, especially on binder, which is slow, but you get the GIF version of this uh, white noise, which is also included here. So you shouldn't see any, patterns here for a good random number generator. If you want to see an example of, the patterns that is not right, you can see it here, for example. Another way to do that is visual analysis with a histogram. So when you generate, for example, numbers between 1 and 100, you can divide them into some, the bins, and then change it into a histogram. If we want to do that, a new plot starting with version 5.2 has a feature that can automatically do that. But we can also process the bins using the C++ thing. I included both versions here for demonstration. To generate the bins. This is the initial code for the color of the things and all the things. This is the C++ bins version. We use an unordered map to count all the bins, for example, here. And this is the new plot bins that we use the new plot features to generate the bins for the histogram. And you can see the output histogram is the same, but there is a simple drift between two versions. The reason of that is that the good thing about the new plot approach is that you can change the bin width and bin start on the fly. But the C++ plus bins, the good thing is that it's faster because you generate the only to send the count number of the each bins to this new plot, so it's much faster. Depending on the situation, you can use one of them, but you can see that with the new plot version, let me do that here. This is the C++ bins version, and this is the new plot version. You can change this bin size on the fly. So if I change, for example, this to 20, it changed the thing. And or you can also change the start bin, for example, like this. Oops. But let's get back to the default ones, because we can also use the feature a smooth K density of the GNU plot to have a Gaussian kernel, approximate of that, of the whole plot. Something like this. So the thing is that when you generate the histograms and for this one, we generated 100,000 and we should get a, rectangle like this for a good engine with a little bit of, changes in the bins. And the reason that this version has these two, part here, it doesn't mean that the random number generated here are not good. The reason is that because of the approximation by Gaussian kernel. So it happens, and I can show you in other, plots that it can, for example, the normal plot that happens. But the last thing that we should know here is reproducibility versus fair play. So the random number generator must be reproducible. It means that using the same seed, you should get the same sequence of random numbers. But the same engine, if you use it in different environment or platform, so for example, if you use the same engine in Windows and Linux, depending on the implementation, using the same seed, you may get different results. But when we say the fair play thing, which is a parallel, comes from parallel Monte Carlo simulations, it means that the hardware, the underlying hardware, shouldn't influence the sequence of the numbers. So if we have an algorithm that plays fair in generating random number sequence, no matter how many processors or hardware you use or the platform, you should always get the same sequence of random numbers. So let's see first how we can generate serial random numbers. Before C++11, there was two functions, one sran to seed the random number and one ran based on LCG generators to generate the next one in the sequence. So the way it was called, it was like this. You can seed, for example, to get the, random numbers on each run, you can seed it with the time, for example, seed this ran with the time, and then call ran to get different sequence. Every time that you run this, you should get different sequence. Oops. I should start with this. So you can see each time, because of this seeding, you get the different sequence of numbers. And if you want to bring them into the range, the common practice was the modulo. For example, this one brings them into the range of 0 to 99. And if you want to bring into arbitrary range between, for example, 5 or 14, you can use this kind of formula to do that. But this is prone to modulo bias, which is very famous thing that happens when you use the modulo operator to bring the random numbers into the range. Here is the explanation of the things. But since C++11, there are engine and distributions to do that. So engines are the source of the randomness, and they usually create random unsigned values. And you use the distributions to bring them into range or generate the different, numbers, or bring them into different numbers of things. So you can have, for example, normal distribution and those things. So here is a simple demo using 4 different approaches. One is for loop to do the same thing. The other one is generate plus lambda and generate plus std bind, and also the generate n. We have all these 4 versions here to compare. So here is the 4, and using the standard library version of, using the algorithm generate to do that, using the lambda. But notice that for the lambda, you should pass the reference to engine and also uniform distributions. And the uniform distribution, as you can see, we asked for 10 to 100, but here both 10 and 100s are included in the output. So you can see that here, for example, in the output, 100 is also generated. And this is the version using the steady bind to bind the distribution and the reference to the engine to pass it here. And this is the final version, which is generate n. The only difference is that here, rather than iterator, you use one iterator, begin, and also the number of elements. All of them generate the same results. But why we demonstrated them here? Because for our parallel version, we use this construct of using of generate algorithm with std bind to generate the parallel random numbers. So let's see that how we can turn this construct into a parallel version. Since C++17, there is a execution policies that allows you to run an algorithm in parallel. The only thing that you need to do is to pass the execution par as a first argument of the algorithm. So let's see if we can use this parallel version of generate to parallelize the whole random number generation using all the standard library facilities. So the thing is that C++11 random engines are not thread safe. So it's not, you can't, send a reference to an engine because this engine is going to be used by different threads and they are going to mess with the, state of the engine. But for the sake of, checking these things, let's just, like the serial version that we had, let's send the on that we use this reference, but because there is a possibility of data race, we just send a copy of that to see what happens. And we add the execution parallel here to see, to make it parallel. If you check the output results, you can see that it's not the thing that we wanted. And this is the randograms generated using the same method for this. This is the pattern that, for example, you get. And if you think about it, it's obvious because when you pass the copy of the engine, each thread with a new instance restarts with the same number in the sequence and producing a repeating pattern. So it doesn't. But for the second attempt, let's send, like the serial version, let's send the reference of the engine to the algorithm and see what happens. If you try that, here, usually on my computer, I get the same results. Let's see here what happens. Okay, let me So this one was the first attempt. But for the second attempt, it takes time. Okay. Okay. Here you can see that it's generate the same. This is on binder. It generates exactly same output. The reason is that because on binder, you are on one core or CPU. So you always get the same sequence. But when it comes to actual parallel, you get the different results every time you run it. And if you generate the randograms, it actually shows that these two randograms are different. But it's not all the problem. The real problem about this approach is that it's even slower than the serial version. So this one, the page generated on a GitHub runner for the GitHub page. GitHub runners are having two CPUs or cores. So let's see the timing here. So serial version took about 83 milliseconds. Oh, but this one is parallel. One is get the same different thing. It's, let me see. Yeah, but it's usually not the case. It's if I run it on the, let me run it on the R server, which has I requested 4 cores if I'm not mistaken. So let's see here what happens. Okay. This one takes a little. Okay, now this is the serial version. So you can see the parallel version takes longer than the serial version. We had 4 cores or CPUs here. So that's the thing. And the reason for that is you know, the problem is with the cache line. Each core tries to access the same cache line as the other cores, and it makes the whole thing run even slower than the serial version. So we have to use a different strategy. There are 4 different ways to do that: random seeding, parameterization, block splitting, and leapfrog. Each one of them have some, the pros and cons. The ones that are working for our case are actually block splitting and leapfrog. The problem with the leapfrog is that it's prone to false sharing. So because the consecutive random numbers are generated by different threads, each one, you know, uh, of these values that are usually on the same cache line are generated with different cores. So because of that, this one is prone to false sharing, but usually for CPU. When you are on GPUs, it's not really important because streaming multiprocessor or SMs have, they are different, and there are lots of, you can, each of them have several cores, and these cores are working on the wavefront of that. And it's not as serious as CPU. So for the GPU version, we can usually use the leapfrog, but for the CPU version, the block splitting is a better choice. So you can also compare the performances here. For example, I can show you here that, so when you use the random setting or parameterization, because it doesn't use the discard of the engine, they run actually a little bit faster because they don't have the over overload of the discard. So this is the serial version. You can see it using the two cores is 100 millisecond. When it comes to random setting, it came down to 30 milliseconds. The reason for that is that probably the GitHub runners have the hyper threading, and OpenMP supports hyper threading. So here, uh, 30 seconds is better than half, and the reason is hyperthreading. And parameterization is more or less the same, but block splitting is 40 milliseconds, and that's because of the overhead of the discard, uh, calling them discard member. So these are the different implementation. The problem with the random setting is that you get always the different results, even using the same seed, because which the threads are unpredictable, and each time they do some part of the sequence, and that's because you get something like this. In parameterization is exactly the same, but here we use the PCG32 because we rely on the special feature of that. And the block splitting, for doing that, we have to have a modified version of std generate or generate n to skip the numbers for each thread. Because of that, we can't use it easily by calling the std generate, and we have to modify this. And this is the thing that actually Ranx does. Ranx provides a modified version of the std generate and std generate n, and it uses block splitting for CPU, running on CPU, and leapfrogging algorithm for generating random numbers on GPUs. And it uses the distributions from TRNG library. The only thing that you need to do to use it is to include the ranks header, which is ranks/random. And the supported engines are currently PCG family. The reason for that is that they provide a discard function that it's the O log n rather than ON. So for example, if you use the engines from the standard library, they may provide a discard algorithm or function, but it's usually the O complexity is ON. So these are the 32-bit generators with 64-bit state, and these are the 64-bit generators with 128-bit state. So they have a larger period. So as I mentioned, you can use the STL engines with the ranks, but they may be slower, and also they may not necessarily produce the same sequence on different platforms. I'm going to add the support for Philox engine, which is going to be in the C++ standard in 26, but I'm going to use a custom version for that. It's something that I'm currently working on that. And Ranx also supported all the 32 distributions in the TRNG library. The good thing about these distributions is that they don't discard values. But distributions from STL, they may do that. And because of that, they may not play fair. So these are all the distributions included in Ranx. And here, changing existing code to use Ranx, to do that, you just need to change all the std, for example, std generate n to Ranx version after including the Ranx header, and also replace the std bind to Ranx bind. This is all you have to do to turn your, code to a parallel version. And for the CUDA and ROCm, there are more. You just need to use a different container as well. For example, device vector rather than std vector. And for one API is also, you have to switch to SQL buffer, for example. But using all these things in Ranx, using the same seed, you get the exactly same sequence. The reason here the sequence is different from the serial version is that in the serial version, we use the Mersenne twister. But in OpenMP version, we switch to PCG32. If you use this PCG32 here, you get exactly same results for that. And to check if it plays fair, here we use the same seed for serial and parallel version. And you can, if you compare these two randograms, you can see that they are exactly the same. If you check some of the patterns, for example, here or there, they are exactly the same. And here is the benchmark that I've already showed you on the running using the 2 cores, but you can also see the results for the 4 cores on our cluster as well. And the last thing is the distribution showcase. I put some of the distributions that included with Ranx, for example, normal distribution, log normal, and Poisson distribution here with different parameters to see, for example, changing mu and sigma to get different plots. And you can see the corresponding code that they generated this using the G3P library. That being said, I think we are at the end of the hour. We can conclude our session now. Thank you.